Hello everyone, welcome back to my class. Today we will talk about concept of coherence. We have already talked about interference, and in the interference topic we have talked about two categories of instrument. One is called the instruments which produce interference fringes using division of amplitude, and other sets of instruments produces the interference fringes using division of wavefront. Okay. Having talked about all these things, we will define what coherence is, what are the different kinds which we will talk about. This all would be addressed here in today's class. Okay. To start with, we will just repeat what we have learned till now about coherence, and then we will slowly dive deep into the coherence definition and its understanding. Now, whenever the two sources vibrate with a constant phase difference, a stationary interference pattern is produced. This we know, yeah. We have two sources, and if the phase difference between the two sources is constant, then due to the overlap between the two sources or between the light emanated by these two sources, we see an interference pattern and which would be sustained. Okay, because these sources are perfectly coherent, because the phase difference between the two sources is constant in time. Now, the two sources which vibrate with a fixed phase difference between them are said to be coherent. Yeah, this we already know till here. Okay. And if the phase difference changes with such a great rapidity that a stationary interference cannot be observed, then the sources are said to be incoherent. Because while studying interference, we talked about these things. We said that if the constant phase difference is not maintained, then the fringes would not be stationary, and if this constant phase difference between the sources is maintained, then the fringes would be stationary. Yeah. Now, for the sources in which the constant phase difference is maintained, we name them as coherent sources, or for the sources for which we are able to get sustained interference fringes, we name them as coherent sources, while for sources which does not produce sustained interference fringe, or for the sources which does not maintain a constant phase difference, they are called incoherent sources. These things we know from our previous lectures. Yeah. Now, the new thing here is that the coherence is categorized in two categories. Yeah, the first one is called temporal coherence and the second is called spatial coherence. Into the coherence properties which are associated with the finite bandwidth of the source comes in the category of temporal coherence. But if the coherence properties are associated with finite extent of the source in space, okay, suppose we are talking about a broad source, then spatial coherence comes into the picture. Okay, we will talk about these two terms more in the coming slides. Now, in the previous lectures on interference, we assumed that the displacement associated with a wave remained sinusoidal for all values of time. Okay, because whenever we write an expression of the field, we just write E is equal to E naught e to the power I omega t minus k z, or E is equal to E naught cos omega t minus k z, and this expression is valid for a monochromatic source, and this expression itself says that the wave is sinusoidal, extending from minus infinity to till plus infinity. Okay. Thus, the displacement was assumed to be given by this expression. Yeah, this is the expression which I was talking about. E is equal to A is the amplitude, cos kx minus omega t plus phi. Phi is some initial phase, x is your direction of propagation, and this represents general electric field displacement. Now, at any fixed particular value of x, the displacement is sinusoidal for all values of time. If you fix particular value of x, then you will see that for all values of time the wave is sinusoidal. Okay, and this is represented here in this figure. In figure 1a, we see that with t we see that the sinusoidal nature of the wave prevails irrespective of the value of t. Okay, such a wave is called monochromatic wave, and the time period is defined here. Yeah, this is the usual definition which we learned in our initial classes. Now, as I said, if you fix x, so let us fix x is equal to 0, then we see the sinusoidal nature of the wave for all values of t. Okay. And this corresponds to an idealized situation, because the radiation from an ordinary light source consists of finite size wave train. Okay. The light which we receive from a source, it is not infinite wave train, it has certain length or certain time duration, and a typical variation of wave train is shown in figure 1b. Okay, then let us go to figure 1b, and in this figure what we see is that a wave is sinusoidal and it is oscillating like this, and then all of a sudden there is a jump. Here you see a kink, and all of a sudden there is an abrupt change in phase and a new sinusoidal oscillation start, and this sinusoidal oscillation sustain till this point, and here again we observe a jump and a new sinusoidal oscillation start. Okay, then here we see there is a phase jump. Okay, abrupt change in phase or abrupt change in the amplitude. Okay. Now, the time during which the wave maintains its sinusoidal nature, it is given by tau c, and this one set of wave is called wave train. Okay. Now, tau c represents the average duration of the wave train, that is, the electric field remains sinusoidal for times of the order of tau c. Okay. Now, we can conclude that at a given point, at a fixed point x in space, the electric fields at time t and t plus delta t will in general have a definite phase relationship if delta t is less than much less than tau c. Okay. If we pick 2 points in time, then those 2 points will be in certain definite phase relationship as long as this delta t the time separation between the 2 time points is much less than tau c. Okay. And these 2 points will never have a phase relationship if delta t is much longer than tau c. Okay. And this is very much clear from this figure also. Now, here if you choose these 2 points, pick these 2 points, suppose this is t and this is t plus delta t, then the separation between these time separation between these 2 points is delta t, and if this delta t is smaller than tau c, which is defined here, then there is a phase relationship between these 2 time point. But if delta t is much larger than tau c, then of course there would be several phase jump which would be there in delta t, and these 2 time points will not be in phase, they would be totally uncorrelated. Okay. Now, this time duration tau c is known as coherence time. Okay. And the field is said to remain coherent for times which is of the order of tau c, and therefore, suppose light is emanating from some source and the wave train has a temporal length of tau c, then this tau c defines the coherence time of the source. Okay. Now, during this time the wave travels c into tau c distance, and this is the length of a wave train. Okay. And this length is referred to as coherence length. The tau c is coherence time and the corresponding length is called coherence length. Okay. And as an example, we can take a neon light whose wavelength is given by 6328 angstrom, and tau c, that is coherence time for this is 10 to the power minus 10 second. And for the red light, red cadmium line, lambda is 6438 angstrom, and for this tau c is 10 to the power minus 9 second, while the corresponding coherence lengths are 3 and 30 centimeter respectively. Yeah. Now, you see that when the coherence time is small, the corresponding coherence length is also small. When the coherence time is large, the corresponding coherence length is also large, yeah, which is very much obvious from this relation, equation number 55. Now, in an idealized source, we will have infinite tau c, but tau c is finite, then what is the origin of finiteness of tau c? Okay. What affects tau c? What limits tau c from reaching to infinity? These limits are listed here. The first is collision with another atom. Okay, suppose an atom is there in a source and then it collides with another atom. Okay, due to this collision there is abrupt change in phase, okay, and that generates kink and that limits the wave train length. The second factor which affects tau c or which limits tau c is random motion of atom. Yeah, the atom moves inside the material volume and that also limits tau c. And the third one is finite lifetime of energy level. Suppose an atom is in excited state and then when it goes down to its ground state it emits radiation, okay, but it only stays the atom, it within some finite time duration it will reach down to the ground state and that also limits tau c, yeah? And therefore, the wave train which get generated will have certain time duration or certain length. Okay. And having talked about these things, now we will see what are the implications, how would it affect the usual interference experiments, and what is the most widely studied experiments, Young's double slit experiment or Young's double hole experiment and Michelson interferometer. Okay. We will implement this knowledge in Young's double hole experiment and Michelson interferometer and see what are the conclusions which we can draw. Okay. Now, here you see usual Young's double hole experiment and there is a source S. Out of this source two sources S1 and S2 are generated and the rays which are starting from these 2 point sources S1 and S2 they reaches to point P, which is on the screen, and at P due to the superposition we observed some fringe pattern. The distance between S1 and P is R1 while between S2 and P is R2. Okay. Now, the interference pattern observed around point P at time t is due to the superposition of waves emanating from S1 and S2, of course. Okay. And since this distance between S1 and P is R, the time which the light takes in reaching from S1 to P would be R1 by C, while the time which the second ray will take from reaching from S2 to P would be R2 by C. Yeah. Now, we are observing the interference pattern at point P at time t here. Okay. At time t the pattern is being observed, but the rays which start from S1 and S2 it takes some time to reach at P. Okay. Then what is the time when it start from S1? The light at S1 start at time t minus R1 by C, while at S2 it start at t minus R2 by C. Yeah, which is very much obvious because it is reaching at point P at time t, therefore, it must have started some time earlier. And what is this earlier time? These earlier times are t minus R1 by C and t minus R2 by C respectively from sources S1 and S2. Okay. Now, we will calculate the path difference. What is the path difference? Path difference would be R2 minus R1. Okay. Now, what is the time to cover this path difference? The time which the light will take in covering R2 minus R1 is R2 minus R1 by C. Okay. This is the time which correspond to the path difference. Okay. Now, if this time is less than much less than tau c, then only the waves arriving at P from S1 and S2 will have a definite phase relationship, and then only we will be able to see proper interference fringes with very good contrast. Okay, I repeat, if the time corresponding to the path difference is much smaller than tau c, which is the coherence time for the given sources, then only we will be able to observe interference pattern of good contrast. Okay. And if the time is larger than much larger than tau c, then the waves reaching at point P will not have any fixed phase relationship and no interference pattern would be observed. Okay. Therefore, at the center, means at this point where R 1 is equal to R 2, in general we will have a good contrast fringe, okay, because the path difference there is 0 and which is of course smaller than tau c. And as we move towards higher order fringes, as we move away from the center, the fringes will gradually become poorer, the contrast will decay down. Why the contrast will decay down? Because as we move away from the center, the path difference slowly increases, and therefore, the corresponding time the light takes to cover the path difference will also increase, and when it will be very close to tau c and larger than tau c, the fringes will start to fade away, and therefore, instead of getting good fringes, we will have this kind of fringes. Yes, slowly it will decay down. Okay. Now, we will implement this knowledge of coherence time in Michelson interferometer experiment. In Michelson interferometer, we know we have a source here, and from this source the light falls on this beam splitter G, and from the beam splitter it goes in this direction as well as in this direction, and then it returns back, okay, after getting reflected, and then the two lights goes into the detector where they interfere and we observe interference fringes. And in this figure, M2 prime is the virtual image of mirror M2, and these two mirrors are separated by a distance d. Okay. Now, the ray, the path difference between the two ray for normal incidence, okay, let me clearly draw it. D is the separation between the two mirrors, yeah, M2 prime and M1. Now, the path difference between the rays which are interfering would ultimately be equal to 2d, twice of d, because the second ray which is getting reflected from M2 mirror or its virtual image M2 prime would have to travel this thickness twice. Yeah, it will go in this direction and then return back, and it is traveling d twice. Therefore, the path difference would be 2d. Okay. Now, how much time the light will take to cover 2d distance? It will take 2d by c second, okay, and therefore, the beam reflected from M1 interferes with the beam reflected by M2, which had originated 2d by c seconds earlier, okay, which is quite correct. Now, again we will implement the same condition. If this time is much less than tau c, then only we will observe fringes, because then the two interfering ray will have a definite phase relationship. Okay. And on the other hand, if 2d by c is much larger than tau c, two interfering beams will not have any definite phase relationship, and we will not be able to observe a interference pattern. Okay. Therefore, we conclude from this analysis is that there is no definite distance at which the interference pattern disappear. Okay, it is not so that it will, there is some critical time or critical path length difference beyond which we would not be able to observe fringes, and before which are at a path length difference which is smaller than that critical value, you will see interference pattern. It is not like switch on and switch off like stuff. Okay. Here, as you gradually move towards tau c, as your characteristic time gradually move towards tau c, the fringes will start to fade up, and if you are far beyond tau c, if the characteristic time or our 2d by c time is much larger than tau c, then fringes will almost be invisible from our eyes. And therefore, we can say that there is no definite distance at which the interference pattern disappears. As the distance increases, distance means path length difference, the contrast of the fringes becomes gradually poorer, and eventually the fringe disappears. Now, the few points which we can note down is that in the Michelson interferometer experiment, the decrease in the contrast of the fringes can also be interpreted as being due to the fact of the fact of the source is not emitting at a single frequency, but over a narrow band of frequencies. Okay, I repeat, in the Michelson interferometer experiment, the decrease in the contrast of the fringes can also be interpreted as being due to the fact that the source is not emitting at a single frequency, but over a narrow band of frequencies. The same concept which we studied in the last slide, that can also be interpreted as that since our source is a narrow band source, our source is not ideal monochromatic source, it has several frequencies, although it is a narrow band, but even in narrow band we have multiple frequencies, and each frequency generates its own interference pattern, and this blurs the overall interference pattern. Now, how does it happen? When the two frequencies, like suppose we have several frequencies, and when the path difference between the two interfering beams is 0 or very small, the different wavelength component produce fringes superimposed on one another, and the fringe contrast is good. Okay. Now, suppose we have a narrow band sources, and the path length difference between the two interfering beams is very small, okay, very close to 0, and if this is so, then maxima and minima of different wavelengths, they fall almost on top of each other. Okay. All the maxima fall on the maxima of other frequencies, and therefore, we see a very good contrast, very good fringes. But when the path length difference is huge, then what happens? Different wavelength components produce fringe patterns which are slightly displaced. Therefore, the maxima does not fall on top of maxima and minima does not fall on top of minima. There would be a slight displacement at which incorporate a little blurring in the fringe, okay, and which are slightly displaced with respect to one another, and the fringe contrast therefore becomes poorer. The poor fringe visibility for a large optical path difference is due to the non-monochromaticity of the light source. The same thing, this is the same reasoning, but it is explained in a different way. Now, let us consider Michelson interferometer, in which the source is having two wavelengths, lambda 1 and lambda 2, and which are very closely spaced. Okay. Now, for two closely spaced wavelengths, lambda 1 and lambda 2, the interference pattern will disappear if maxima of one falls on the minima of other. Suppose it is normal incidence, it is equal to integral multiple of wavelength here, then suppose it is m lambda, okay, and suppose it is for first wavelength. For second wavelength, 2d is equal to m plus half lambda 2. Okay. Now, take the difference between the two, then what you will get? You will get the following: 2d by lambda 1 minus 2d by lambda 2 is equal to half. Okay. This is the relation which is written here. For normal incidence, for two wavelength, if maxima of one falls on the next or successive minima of other, then you will have this condition, and you will not see any fringe pattern. Okay. This is what it is said here. For two closely spaced wavelengths, lambda 1 and lambda 2, the interference pattern disappear if this relation holds. Okay. And from here we can get expression of the path length difference, which depends upon the wavelength and on their separation. Okay. Since lambda 1 and lambda 2 are very close, we can replace lambda 1 into lambda 2 with lambda square, where lambda is average of lambda 1 and lambda 2. With this in hand, let us do it differently. Now, instead of two discrete wavelength, if we assume the beam consists of all wavelengths lying between lambda and lambda plus delta lambda. Yeah. Earlier we took only two discrete wavelengths, lambda 1 and lambda 2. Now, we are considering that we have a source which is emanating a beam and which have several wavelengths, a continuum of wavelength, and this continuum of wavelength lie between lambda and lambda plus delta lambda. Okay. Two limits are there. The first one is lambda and the second is lambda plus delta lambda, and between these two wavelengths all the wavelength component are there in our beam. Okay. Then the interference pattern produced by the wavelength lambda and lambda plus delta lambda by 2 will disappear if this relation holds. Okay. What exactly we are doing is, here we consider two wavelengths lambda 1 and lambda 2. Now we are considering a band of wavelength, okay, and this band extend from lambda plus delta lambda. Now what we are doing is that we are picking two values of wavelength in this band. The first one is lambda and second is lambda plus delta lambda by 2. Okay. And we want these two the interference pattern between these two wavelength, this is first wavelength and second wavelength, between these two wavelength we want the interference pattern to disappear. Okay. And when will this appear? When will they disappear? They will disappear when they satisfy equation number 61. Okay. Now let us replace lambda 1 by lambda and lambda 2 by lambda plus delta lambda by 2 and then get this expression. Okay. Therefore, the interference pattern produced by wavelength lambda and lambda plus delta lambda by 2 will disappear if they satisfy equation number 61. We substituted the expression of lambda 1 and lambda 2 in expression 61 and we got this expression 62. Okay. Now we have a band which start from lambda ends at lambda plus delta lambda, and out of this band we picked two wavelength lambda and delta lambda by 2, and these wavelength will, the fringes for these two wavelength will disappear if the path length difference 2d is equal to lambda square upon delta lambda. Okay. Now for each wavelength lying between lambda and lambda plus delta lambda, there will be a corresponding wavelength lying between lambda plus delta lambda by 2, this is extra written, and lambda plus delta lambda. Okay. Now what I am saying is that we pick two wavelength which is lambda and lambda by delta lambda by 2. Now for each wavelength lying in this band, there will be a wavelength lying in this band for which equation number 62 will be satisfied, or alternatively for each wavelength in this band there will be a corresponding wavelength in the other half of the band which extend from delta lambda by 2 to lambda plus delta lambda. Okay. Sorry, this is lambda plus delta lambda, yeah, this is lambda plus delta lambda. Okay. This width is delta lambda by 2, but the value of this wavelength is lambda plus delta lambda by 2. Okay. And similarly this width is again delta lambda by 2, but the value of wavelength is, here it is lambda plus delta lambda by 2 and here it is lambda plus delta lambda. Yeah. These are the two bands. Okay. The first band extend from lambda to lambda plus delta lambda by 2 and the second extend from lambda plus delta lambda by 2 to lambda plus delta lambda only. So for each wavelength in this band there exists a wavelength in the second band such that minima of one falls on the maxima of other, and this produces no fringe. Okay. This disappears the fringe. Okay. Now therefore, as long as 2d is much larger than or equivalent to lambda square upon delta lambda, the contrast of the interference fringes will be extremely poor. Okay. I repeat, as long as 2d is larger than or equal to lambda square upon delta lambda, the contrast of the fringes would be poor. Okay. The corresponding spectral width of the source will be delta lambda is equal to lambda square upon 2d. Till now we were only talking in terms of path length difference or the time which the light take in covering the path length difference and the coherence time. We were only relating these two terms, but now the similar condition can also be imposed on the spectral width of the source. And what is this condition? This condition is given by 64. Okay. And it says that if the contrast of the interference fringe becomes very poor, when the path difference is d, then the spectral width of the source will be lambda square upon 2d. Okay. The spectral width must not be larger than or equal to lambda square upon 2d. Okay. If the spectral width is satisfying equation 64, the fringe pattern would be very poor. Okay. The wave delta lambda must be smaller than the right hand side quantity in equation number 64 to have very good interference fringes. Okay. But and we observed that if the path difference exceeds the coherence length, the fringes are not observed. This is the same statement. Okay. Either you say that path difference must not exceed coherence length, or the time taken to cover path length difference must not exceed the coherence time. Okay. The same thing. Therefore, the spectral width, which is delta lambda, which can also be written as lambda square by L. Okay. You see here delta lambda is equal to lambda square upon 2d. What is 2d? 2d is optical path difference, and optical path length difference is a length which must be smaller than coherence length. Okay. The maximum value is capital L, which is coherence length. Okay. And if it goes beyond the coherence length, fringes will start to decay down. Okay. Therefore, we can write delta lambda is equivalent to lambda square upon L, which is equal to lambda square upon c into tau c, okay, where L is capital L is equal to c into tau c. Okay. Thus, the temporal coherence time tau c of the beam is directly related to the spectral width, which we also call as line width. Okay. Once a source of given line width is given, then we can quickly predict its coherence time using this relation, okay, using equation number 65. Now, once we know the relation between wavelength width and coherence time, then we can quickly calculate the relation between delta nu, the frequency width or frequency spread with the coherence length or coherence time. How to do this? We know that frequency nu is equal to c by lambda. Then delta nu, which is frequency spread, it can be calculated by just taking the derivative of this relation, and from here we get this relation between frequency spread and coherence length. Okay. The sign we have neglected because it does not play any role here, we are just interested in the numbers. Now, since tau c is L by c, we substitute the expression here, then delta nu is inversely proportional to tau c, the coherence time. Therefore, the frequency spread of a spectral line is of the order of inverse of the coherence time. Okay. It means that once we are given a source, we know its central frequency or central wavelength and its bandwidth, be it delta lambda or delta nu, then we can quickly calculate the coherence time. Okay. The quantity delta nu by nu is called monochromaticity of the source or spectral purity of the source. Okay. And one can see that even for ordinary light source, it is very small. Okay. Delta nu by nu is very small for ordinary light source, but if we talk about lasers where delta nu is very small, then this spectral purity increases. This is all for today. Thank you for listening me.